So this is a nice perspective article, which means some experts are getting together and telling us how some things need to happen, what is the state of the art, where we need to go, what we need to get it done, education, training. In this case, it's near-term ecological forecasting for climate change action. Near-term has a specific meaning in this sense. It's not weather, 1 to 3 days, multiple weeks, sub-seasonal as we call it, or seasonal to interannual climate predictions, but this is about multi-year to decadal predictions as opposed to projections which go out to multiple decades and they need scenarios and so on and so forth. It's a very detailed article with a lot of references. I'm going to make it very short and take the best points that I think are worth reporting to you, but obviously the paper is very good and you can go back and read it if you are interested in more details. So this is talking about a substantial increase in predictive capacity that is needed to anticipate and mitigate the widespread change in ecosystems and their services in the face of climate and biodiversity crises. Everybody is using this word crisis. I'm not sure we are being very rigorous about it, but you know that there are a lot of climate impacts on ecosystems, biodiversity loss because of climate change as well as because of direct human activities, urbanization, agriculture, deforestation and so on, also in the oceans. But here let's see what we are going to talk about. In this era of accelerating change, we cannot rely on historical patterns or focus primarily on long-term projections that extend decades into the future. In this perspective, we discuss the potential of near-term, so daily to decadal. This is their terminology of near-term. And it is iterative ecological forecasting to improve decision making on actionable timeframes. We summarize the current status of ecological forecasting and focus on how to scale up, build on lessons from weather forecasting, and take advantage of recent technological advances. As I said, it's a perspective that's going to say where we are, where we need to go, what we need to do that, how can we take advantage of the knowledge we already have, so let's say from weather forecasting and so on. And we also highlight the need to focus on equity, workforce development, and broad cross-disciplinary and non-academic partnerships. And it's going to be international. We may touch on it a little bit. I've taken the main points as I said. So workforce, to make sure that we can implement these forecasts into action to protect biodiversity, equity, so that everybody can benefit from this effort. And especially because biodiversity has a lot of livelihoods that depend on biodiversity, so you have to protect them as well. And cross-disciplinary and non-academic, because you are going to not just be dealing with other scientists from any discipline, but actually people on the ground, decision makers, policy makers, stakeholders, and so on, right? Just to read some upfront introductory material, the dual climate and biodiversity crises jeopardize our ability to manage and conserve natural resources and sustain socio-economic systems. Impacts are already being felt across all levels of society, from individuals to nations, and many of the world's ecosystems are at the risk of collapse. Again, these are words that you have to see what it means. How do we measure how close we are to collapse and so on? It's always important to make sure that there is some rigor, but there are references which tell you where these ideas come from. Indeed, when considering the most severe risk facing society over the next 10 years, the World Economic Forum ranked environmental changes as the top 4 most severe risks, and they comprise 6 of the top 10. No question about that. In the face of accelerating change and increasingly frequent extreme climate events, responses to these crises cannot continue to be focused primarily on projections that extend decades into the future, so out to typically 2100, and I have railed against this quite a bit also. Similarly, historical patterns, for example, of species, ranges, fire, drought, flood frequency, etc., can no no longer be relied on as the primary basis for environmental decision making. Steady state solutions do not work in a world dominated by non-equilibrium transient conditions. Society is in uncharted territory. Moving forward requires new approaches to research, management, and decision making, in this case specifically focusing on near-term ecological forecasting for societal action. So what do they mean? Near-term iterative ecological forecasting. In the top here we are looking at ecological forecasting that provides qualitative predictions of how different management scenarios impact the environment on decision relevant timescales. This is very critical, decision relevant timescales. 2100 projections, what good are they? What are the uncertainties in them, and so on, raise serious questions. So without ecological forecasting, we are in a gray zone. Uninformed decisions affect everything, and we don't know what the intended and unintended consequences are, because decisions are always taken with some intention. With ecological forecasting, everything is looking good. So decisions happen, but you have iterative processes. So decision makers can go this way or they can go this way if we give them enough information to make informed decisions at decision relevant timescales. Okay, so 2100 projections should not become a way to avoid taking decisions, right? Avoid making decisions. So what is the iterative learning loop then? You have society and science sitting in the middle, relevant forecasts that improve lives and livelihoods, and science understands patterns in predictability in nature, including emergent solutions with climate change. So you can start anywhere. Real-time environmental data, leverage data sources such as NEON, which is an observation system that I won't talk about here. Computation, harnessing the data revolution. Earth system predictability, so at various scales. Earth system here means not just climate, but actually ecosystems, ecosystem feedbacks, carbon cycle, and everything. Clarity and insight is needed, so diverse catalogs of forecasts improve science while helping society. That's where the iteration comes in. And decision makers understand the context in which this information is produced and what the implications are of making better decisions based on this information, which comes with clarity and insight, and then back to what real environmental data will be needed to make this whole loop better. That's where the iterative ecological forecasting comes from. NEON is given here, National Ecological Observatory Network. Okay, so these are iterative ecological forecasting that involves continually updating predictions with new data. Moving forward, jumping forward, in fact, near-term iterative ecological forecasting has the potential to anticipate ecological change at the scale and speed needed by society. There is a lot of literature on the speed of change or velocity of change, things moving latitudinally as things warm, as climate warms up, moving up the mountains, who can move, who can not move, ecosystems don't move, species move, and so on and so forth. Such forecasts provide predictions and scenario-based projections about the future state of ecosystems and their benefits to people, with fully specified uncertainties that are continually updated as new observations become available, as we saw in this iterative loop here. In contrast to long-term projections, near-term forecasts on daily to decadal timescales are more closely aligned with the timescales that are most relevant to environmental management, and thus allow society to anticipate changes and improve decisions on actionable timeframes. Actionable forecasts present decision makers with a range of predictions and in some cases projections under different decision alternatives or climate extremes, with clear statements of forecast confidence and uncertainty that can be propagated into the decision analysis so that you can stay in the loop and keep improving the entire system. Jumping ahead, what is the global demand for ecological forecasts then. While much past work on near-term ecological forecasting has focused on local to regional scale environmental issues, meaningfully contributing to international environmental goals and initiatives will require ecological forecasting to scale up to global issues. So biodiversity is not always a local issue, even though it has got a lot of local components and local region specific, location specific climate feedbacks, etc. One place to start is forecasting the flows of mass and energy through terrestrial and marine ecosystems, as they are already present in most of the Earth system models that are part of the coupled model intercomparison project CMIP, which in turn forms the basis for IPCC reports and projections like the Assessment Report 6 that is the latest one. Next generation Earth system models already include a wide range of ecological processes such as vegetation, demography, microbial biogeochemistry and disturbances, and also ecosystems such as lakes, rivers and wetlands, urban and agricultural, etc., as well as a more explicit representation of biodiversity. But these global models have primarily been applied to project long-term climate responses. So far they have been underused at shorter time scales where if they are properly initialized and propagate uncertainty, there are opportunities to inform climate adaptation, mitigation, carbon monitoring, and the UN Sustainable Development Goals such as hunger, disease, water quality, sustainability, climate action, and terrestrial and marine biodiversity, and so on. So it is basically initialized forecasts versus projections with scenarios, which are free integrations starting typically from pre-industrial levels of CO2 and other land use types, and then increasing greenhouse gases and volcanic eruptions, solar activity, and so on. So initialized predictions are very different than these free integrations through historic periods into the future with scenarios, right? We've discussed this elsewhere, you can look up. For example, ecological forecasts could be incorporated into the UN's early warnings for all climate adaptation initiative, which I have discussed elsewhere, which focuses on global equity in forecasting, risk management, communication and preparedness activities from a weather and water perspective. Okay, it's focused on all sectors as I've discussed elsewhere. So I don't want to go into all the details, but there are actually many ecological forecasts already that rely heavily on data sets that are international in scope, because there are coordinating bodies under the World Meteorological Organization and the various programs under it, like FluxNet and GLEON and so on. And there are groups on Earth observations which are monitoring and data sharing. There are protocols on how to do this. Countries become members, they contribute, they get benefits from it, and poor countries are helped by the richer countries, and so on and so forth. Similarly, efforts to build on ecological forecasting community, which includes community coordination on training, tools, standards and synthesis, have primarily been grassroots operations. So there is a blurb on state of ecological forecasting that you can read. So international growth in focus and investment has not been distributed equally, however. So, the rich people tend to rule these things, and sharing is quite democratic, but not everybody benefits unless they are in the network of some sort. Investments in ecological forecasting, so development, training, data collection and so on, are critically needed to deliberately address historic and current inequities both within and across nations, and to support efforts led by indigenous peoples. They have a lot of knowledge that is not typically integrated into science and scientific modeling and decision making and so on. So what are the scientific acceleration and grand challenge questions? I'm jumping a lot of details on the perspectives that the authors provide, okay? So please go back and read if you want more details on every aspect of this. The cyclic nature of iterative forecasting aims to establish a learning loop in which predictions can be meaningfully compared with new observations, and the models can then be updated to improve future predictions, as we saw in the iterative loop. This approach is central to the idea of adaptive management, which emphasizes the importance of evaluating and learning from the outcomes of previous decisions to inform future decisions. So you have complete flexibility and adaptation, adaptive management, learning by doing, and so on. Okay, so already the examples exist for this. So the ecological forecasting cycle can be a win-win, simultaneously improving decision making while accelerating scientific understanding. This is possible because well executed ecological forecasts are specific and quantitative and thus falsifiable, so they have to be validated, updated, skill and uncertainty has to be quantifiable, and so on. So they provide continuous real-time feedbacks, and you can do it in many cases using, both decision focused and basic science questions can be addressed with these, helping to align the needs of the two fields of the ecological research community. For example, forecasting, so basically protecting and decision making to protect against climate change. Okay, all the ecological hypotheses embedded in the forecasting models can have a real-time feedback to make sure we are not misrepresenting anything, that we are constantly updating our knowledge and forecasts, right? So forecasting lake and reservoir ecosystem is used by drinking water reservoir managers to improve water quality in the face of non-stationary climate variability, while scientists are using the same forecast to improve understanding of freshwater ecosystem dynamics. More broadly, comparative analysis across forecasts for different systems have the potential to answer grand challenge questions about the predictability of nature itself. How far into the future can different aspects of nature be successfully predicted? Why do some ecological systems respond to climate change more predictably than others? When are ecological forecasts limited by the quality of other forecasts such as weather? That are commonly used as model inputs? Is ecological understanding transferable across systems, or is it very local and region specific? What do the answers to these questions tell us about the overarching rules and patterns in ecology? So science questions, decision questions, biodiversity preservation, protection questions, restoration as well, and so on, right? So existing theory about ecological predictability has focused on two key metrics. One is the rate at which forecast uncertainty grows with time, just like in weather, can become chaotic in a few days. And secondly, the limit at which the forecast accuracy is no better than chance, just like saying next year will be the same as this year. Climatology, right? So our previous work showed that the uncertainty growth rate is a function of uncertainties in 5 key inputs and the sensitivity of the forecast to each of these inputs. Atmospheric scientists used this type of uncertainty decomposition in the 1960s to determine that weather forecast uncertainty was dominated by uncertainty in the initial conditions. A theoretical advance that has guided large-scale investments in terms of billions of US dollars per year in weather monitoring, modeling, and data assimilation that aim to constrain the initial condition uncertainty in each new forecast. So this is the famous Ed Lorenz work. The Lorenz model has been used ad infinitum to learn many things about how small errors in initial conditions can grow into large errors in forecasts and so on in a very non-linear system like the weather system. These investments have driven decades of continual improvements and so on. And ecological forecasting is now poised to make similar leap in foundational understanding. So we are behind, but we can catch up. Understanding which sources of uncertainty dominate. So what are the key drivers of uncertainty? While some ecological forecasts are like weather, highly sensitive to initial conditions, others are dominated by sensitivity to other uncertainty in external drivers such as climate change, model structural or process uncertainties, data limitations in constraining model parameters, and inherent variability of biological systems. So the rate parameters in biology, photosynthesis, grazing, predation, whatever, growth, and so on, can be very hard to measure and include in the models as parameterizations either. So Understanding which sources of uncertainty dominate which ecological forecasts is critical to deploying effective monitoring, modeling, and model data integration efforts. Furthermore, unlocking the grand challenge of understanding the patterns of predictability in nature will require a comparative approach across the diversity of ecological systems to quantify which ecological forecasts are limited by which uncertainties, ultimately being able to anticipate which ecological systems will be predictable and what information will be needed to constrain new predictions will drive improvements in our ability to make decision relevant forecasts and decision makers' ability to make better and more confident decisions. So it's an iterative process. So what can we learn from meteorology while addressing unique challenges? I won't go too deep into it, but you can guess what they are. Ecological forecasting has much to learn from other forecasting communities that are deeply embedded in decision making, whether forecast is now 100 billion or more bigger industry. For example, decades of progress in meteorology demonstrate that reliable predictions are possible for complex natural systems if iterative approaches are adopted. Meteorology also illustrates the potential for both open provisioning of public goods such as climate data, weather forecasts, severe weather alerts, and private sector innovations such as broadcast meteorology, weather apps, artificial intelligence, augmented forecasts, and so on. So now weather forecasts are applied to food, agriculture, water, health, energy, buildings, infrastructure, and so on. Right? So weather forecasts are more than just outputs from weather numerical models. Multiple times a day at meteorological centers around the world, weather models are iteratively updated with new data from a globally connected network of satellite and ground sensors, and new predictions are generated from updated models. Ecological forecasting should build on this framework by continually updating forecasts as new data become available to provide decision makers with the best available scientific insight, accelerate scientific discovery, and improve understanding of ecological predictability more broadly. The user base for weather grew over time, and now people pretty much expect to look at weather several times a day, and they make many decisions based on weather forecasts, and they have internalized on how to interpret the uncertainties of, let's say, 30% rain versus 60% rain, and so on and so forth, right? For what to wear, when to take a break, whether to go to the beach on the weekend, and so on and so forth. So state of the ecological forecasting community then. Dramatic improvements in ecological forecasting are now emerging that were unimaginable even a decade ago. Advances in sensor technologies, satellites, and genomics provide access to unprecedented volumes of environmental data that are born digital and increasingly near real time. The urgency of climate change has driven shifts toward large-scale networked science, which in turn has made data access more standardized and equitable, both in terms of top-down international observatories such as NEON that we talked about, and bottom-up globally distributed experiments with standardized protocols that I won't read about in terms of all the acronyms here. At the same time, there have been rapid advances in computational methods and cyber infrastructure, including revolutions in artificial intelligence and machine learning, workflow centralization, distributed cloud computing, and cloud native data storage. Collectively, these advances have fueled the recent growth of ecological forecasting and herald opportunities for further increases in scope and research. What is the way forward? I have a bunch of more text to read, but it's okay. Responding to pressing global environmental challenges in an era of climate change will require substantial local and global development to scale up the ecological forecasting enterprise. Rapid progress has been made, particularly over the past 5 years, as efforts to bring together the community have accelerated. Meeting this challenge requires an intentional and inclusive approach to build the human dimensions of our forecasting capability. The translation of forecasts from research to societal impacts has required new cross-sector partnerships that span academia, governmental agencies, industry, NGOs, and other interested parties to be established. Furthermore, the technical requirements for building operational ecological forecasts often exceed the capacity of governmental agencies, such as the traditional producers of forecasts. For example, the soil carbon monitoring being conducted by the nascent carbon credit industry, which serves as both a key input and validation of their carbon forecasts to inform climate mitigation, is already on track to surpass the data volumes in government agency soil maps. So once people see soil as a way to put away carbon, then it can serve as a good offset. Of course, it can also help with a virtuous cycle towards nutrient retention, soil moisture persistence, crop yield increases, farmer incomes, and so on. While efforts like EFI have laid the groundwork for building bridges across sectors, for example, through interagency and cross-sector workshops and training. In scaling up ecological forecasting, there is an important need to foster even greater innovation and engagement across a broader spectrum of partners, end users, and decision makers. Key to these partnerships is the idea of co-production, which is now very commonly used as a way to make sure stakeholders are engaged. Groups that will use forecasts need to be engaged in the process of launching new ecological forecasts from the outset by informing and contributing to the goals, approaches, and product design. These partnerships and the associated scaling activities must acknowledge historical biases in participation and perspectives, such as the advantage to the global north in general, and actively promote equity in participation and recognition of marginalized perspectives going forward. Such co-production is necessary to ensure that ensure that forecasts are equitable, usable, useful, and credible. So I forgot what EFI is. Ecological Forecasting International. I should remember, but when you read these papers, there are so many acronyms that you tend to forget some, and I should write them down, but I usually don't. There are obviously many EFIs. EFI is Ecological Forecasting Initiative. So I was thinking whether it's international or initiative. There we go. Sorry about that. Let's continue. I hopefully am still recording. Yes, I am. And I'm at 27 minutes, but that's okay. All right. So with that, the last part, one key part of community building is engaging groups that have been traditionally excluded both from science and decision making. For example, scientific research funding in the United States goes disproportionately to white principal investigators, and racial minority groups earn a disproportionately low fraction of US earth science doctorates. There are lots of details here, but let's just read through. At the same time, many of the world's environmental problems disproportionately impact members of marginalized groups, including indigenous communities and urban poor. This is discussed in many papers across the literature and reports and so on, where poverty can trap you into a catch-22 that you can never get out. Furthermore, while ecological forecasting is global in scope, low and middle income countries are underrepresented in both research and community participation, despite absorbing a disproportionately large share of the world's biodiversity, carbon storage, and climate impacts. Active investment by international bodies in building of ecological forecasting capabilities in the global south, much as the World Meteorological Organization has historically done for meteorology, would help to address both these inequities and international climate and biodiversity and sustainability goals. It's essential to actively ensure that our work not only broadens participation among these groups, but also helps identify and address the underlying structural issues that create and sustain their underrepresentation in the first place. Lots of them tend to be implicit biases. People argue also that the IPCC scenarios are basically dominated by the West and the global North, and the interests of the global South are not really included in those scenarios. So, in conclusion, ecological forecasting is at a critical point for future growth, similar to weather forecasting in the 20th century, and cannot afford to step back. Stepping forwards requires a quantum leap in forecasting capacity, game-changing scientific breakthroughs, and technological developments, and a new 21st century vision of data-driven environmental management. The nations of the world, along with the UN bodies, major international corporations, and NGOs, can help by integrating ecological forecasting into their climate adaptation and mitigation strategies. At the same time, the scientific community spanning academia, agencies, and industry can help build capacity to respond to this urgent need. Ecological forecasting simultaneously offers a new set of tools to advance these efforts and a new frontier of discovery about how nature works, making forecasts of nature mainstream and developed by diverse sections of society will generate the foresight to mitigate further degradation and enable us to proactively build a future that is climate resilient and nurturing for people and the planet. There are a lot of co-benefits in terms of health and mental well-being and so on, of protecting ecology, biodiversity, and of course livelihoods of the people as well. And who doesn't like a walk in greenery, forests, etc.? So overall, it's a very good idea. There are many details I skipped, but you get the gist of the idea of the observational needs, the forecasting tool build up, and the iterative process with which stakeholders, decision makers, corporations, NGOs, etc. can get involved, so that we can accelerate the ecological forecasting in near term days to a decade, to catch up with weather forecasting as well, right? So let's leave it here for now.